So like how you have this Coulomb's law to find the force. Is Coulomb's law applicable only to find the force? It is also helping us find something else. It is also helping us find the electric field due to a point charge, if you remember. E is equal to F by Q, but in the place of F, you applied Coulomb's law. KQ Q naught divided by R square divided by Q naught. Q naught gets cancelled. KQ by R square. Now, the question is, what if the system gets extended to being more than a point charge, right? Like if you have a linear charge distribution, for instance, then I'm interested to calculate the electric field due to this kind of a system, right? So positive, like this, I take a system. Now, electric field is always calculated at a point. So if I take the point here and if I take this distance to be r, am I clear with this? So if I need to apply Coulomb's law and then solve this, what I'm supposed to do is, I'll give you a perspective of this. See, I need to take a small charge dq. Due to this dq, I need to find the value of electric field at this point. You understood why I drew the arrow mark away? Why is it so? Because it's a positive charge, right? So due to this dq, I'll find what is the value of the small electric field. It's also called as dE. Then I need to integrate it from one limit to another, which is slightly a tedious process. And as I mentioned, that is not a part of your syllabus as well, at least for CBSE, right? Now, for these kind of charges, is there a possibility where we can take the help of symmetry and find the electric field in lesser number of steps? That is where this Gauss law comes into picture. Where the advantage of this Gauss law is, it takes the concept of electric flux into consideration. So there are two parameters that you need to know. One is you need to know what is electric flux generated due to the system, and what is the total amount of charge enclosed within a surface. The name of the surface, I'll reveal it. Okay, what are the two things? What is the amount of electric flux that is associated with the closed system, and what is the amount of charge that is present within the closed system. So having said this, let's first try to understand the definition of it. So what does it state? It states that it relates the flux. Here the flux means electric flux. Gauss law is applicable for electric and magnetism also. Okay, so there the flux will be magnetic flux. So listen to this carefully. The law relates the flux through any closed surface and the net charge enclosed within the surface. Right? I hope this point has got registered in your mind. So having said this, let's see how they are related. If you take the total electric field E over any closed surface, right? The total electric, there is a mistake here. It is not the total electric field, it is the total electric flux. Okay, correction. So the law states that the total, oh, I'm sorry, they mentioned flux here. Sorry, I didn't see that. So it states that the total flux of the, I need some more practice. It states that the total, what is happening? I understood what is the issue, but it will take some time to resolve. Pen came up. So the law states that the total flux of the electric field over any closed surface, this closed surface I told you, no, it is called as Gaussian surface. So the total electric flux over any closed surface is taken to be equal to 1 divided by epsilon naught. Okay, epsilon naught is the permittivity of free space. 1 by epsilon naught times the total charge that is present within the closed surface. It's a simple statement. You know the total flux through a closed surface. You know what is the total charge through the closed surface. Okay, so that's what they told, no? How is flux represented as? With the symbol phi. So if you know the total flux through a closed surface, this will be equal to what? 1 divided by epsilon naught times the charge enclosed by the Gaussian surface. This is the mathematical statement. With this, you will see you can find the electric field in very less number of steps. Okay. So this flux is there. Now, what is the formula I told you yesterday? It is E vector dot A vector. E vector dot A vector is equal to charge enclosed divided by epsilon naught, right? Now I want to introduce one more thing here. See, this E dot A, you can write it if you directly know the value of electric field and you know the value of the areal vector, right? But there will be scenarios where you don't know the areal vector completely. At that time, what we are supposed to do is, flux is written as something like this, integral with a circle around it, which we call it as loop integral. So when you talk about integral, no, there are two things. One is like this, which is called as line integral. This is what you would have seen in your 11th standard when you derive the formula for equations of motion. It's called as line integral, whereas this is called as the loop integral. So, or surface integral kuda solluvaanga. So it's called as surface integral or loop integral. It is given as E vector dot, instead of A, right, you will have dA vector. So the surface integral of E vector dot dA vector is also going to give you the total flux. This is what we are going to use in the applications of Gauss law, which I told you yesterday. There are 3 applications I told you, no? There we'll use this expression. Am I clear with this? But everything relates to the same concept of flux. So can you people tell me the statement of it? Just put it in one line and tell me the total electric flux through any closed surface is equal to 1 divided by epsilon naught times the charge enclosed by the closed surface. That's it. Okay. So this is the mathematical expression. Write it down. You will integrate the area itself. Generally, when you put a line integral, you get area. Line integral output is an area. Similarly, loop integral's area will be volume. Double integration, Mary, but it is not like actually loop integral. I'm sorry, I have to correct. This is you're integrating the area itself. There, you're integrating one dimension. For example, you will integrate something like lambda dx. X refers to length. Okay, you're integrating a one-dimensional parameter, whereas here you're integrating a two-dimensional parameter. Okay, so when I do the derivation, you will understand how the values will come out. So we discussed about the closed surface. No, that what is the name of the closed surface? We call it as a Gaussian surface, right? So basically, this is something that does not exist. It is something that is imaginary. It is an imaginary surface which is drawn around the charge distribution that is given to us. So whatever is the shape of the charge distribution they have given. See, we discussed about 3 main types. Those are all uniform charge distribution, but there is a possibility where something can be non-uniform also. Like you can have a charge that is distributed in some shape like this, who knows, right? So when you have something like this, right, for us to apply the Gauss law, we need to consider a closed surface, right? And that closed imaginary surface that we consider is what is called as Gaussian surface, and mostly it is a 3-dimensional figure. It's mostly a 3-dimensional shape, right? And here, see, if you read this note, right, one point that we need to concentrate upon is Gauss law tells us that the flux through any closed surface S, if you name the closed surface as S, depends only on the value of the net charge inside the surface and not on the location of charges outside the surface. So, sorry, and not on the location of the charges. And the next point is charges outside the surface will not contribute at all. Listen to this point carefully. What I'm trying to say is, if I say I have a point charge like this, if I take a closed surface like this, which I call it as the Gaussian surface, then this is going to have the field lines in this way. Am I right? Right. So here, if I take the sphere of radius r, let's say the flux is coming out to be phi. Now my question is, what will happen to this flux if I increase the radius of the sphere from r to 2r? So logically, what should happen? Flux should decrease. How many of you say decrease? Okay. Whatever is your gut feeling, just raise your hand. You're saying decrease. How many of you are saying increase? What are the others saying? Don't know. Jesus will take care. எப்படின்னு என்னது? Huh? Nothing should happen actually. It should not change. It should not change. So, if this is R, if you increase the size of the Gaussian surface to whatever value you want, it is still going to be the same. Because you can apply two logics to it. One is, you see the number of field lines that are going is the same. I know where you got confused. Thing is, if I take my hand and keep it like this, that area, if I keep moving, it will change. But this Gaussian surface is considered in such a way that it is covering the whole charge. That is what the first point says. So there is one often asked question, right? They often ask this, and most of them write it as 2π. No, flux has nothing to do with the radius of the Gaussian surface, the size of the Gaussian surface. What does it depend on? It depends only on the total charge that is present within the Gaussian surface. If it is Q, and due to this Q, if there is a flux that is going to get generated, according to Gauss law, what will be the value of flux that will get generated? Charge enclosed divided by epsilon naught. So, is there anywhere this flux is dependent on the radius mathematically? Nowhere. What does it depend on? It depends on epsilon naught, which is a constant, and Q is the total charge which is inside the surface. Similarly, if I have a system like this, if I have a positive charge here, if I have a negative charge here, then what is going to be the total flux through this surface? If I take the value of this as Q1, if I take the value of this as Q2, for instance, then what is going to be the flux in this scenario? It will be Q1 divided by epsilon naught plus minus Q2 divided by epsilon naught. Am I right? Tappu. What is the second point saying? It depends only on the charge present inside. Outside charge has nothing to contribute to the flux. Common mistakes. So what should be the answer? Q1 by epsilon naught should be the answer. Right? One last question. So if I take this kind of a system, Q1, Q2, Q1 positive, negative Q2, positive Q3, right? And outside you have Q4 and minus Q5. What is going to be the total flux through this kind of a surface? Q1 minus Q2 plus Q3. That's it. So what did you apply here? You applied some property. What is the name of this property? It's additive nature of property. I told you, you will apply it at the later part of the chapter. So additive nature of charge divided by epsilon naught. So outside charges we are not concerned at all. Let it be infinite number of charges also, right? These are two important points you need to have in mind. Did you understand the application of these 2 points? Make a note.